This is the last part of Chapter 6, mean and standard deviation for a binomial random variable. So the mean, or again the expected value, and the standard deviation for a binomial random variable. So this is specifically for a binomial random variable. The mean and the standard deviation formulas are both on your formula chart. So the mean is n times p, and the standard deviation is the square root of n times p times 1 minus p. So we're going to practice using both of those for a binomial random variable. So for a discrete random variable, that's when you have a chart. In a binomial random variable, you're just going to have n and p. There's not going to be a chart. Alright, so this is n times p, and this is the square root of n times p times 1 minus p. So let's look at an example. It is known that 41% of all households are wireless only. That's the example we've been working with. In a random sample of 300 households, that's our n, how many would you expect to be wireless only? So we're going to do n times p, that's 300 times 0.41. And we kind of looked at this back in Chapter 5, where you do your sample size times what you expect to happen. So 300, we expect 41% of that 300 to be wireless only. So that would be 123. So we expect 123 out of the 300 houses to be wireless only. And then what is the standard deviation for this distribution? We're going to do the square root of n times p times 1 minus p, which is, now n times p is the same n times p we just calculated, so you don't have to do that again, but you can. It would be 300 times 0.41. Remember, your proportion is always as a percentage, and 1 minus 0.41. So you can type all that in at the same time. 300 times 0.41 times 1 minus 0.41. So the 1 minus 0.41 needs to go in parentheses. The rest can be like that. In the newer calculators, the square root bar goes all the way across. In the older calculators, it opens a parentheses. So you'll type it in just like that, and you'll close that parentheses. So 300 times proportion 0.41 times 1 minus 0.41. That's the part that has to be in parentheses. And then you'll close the parentheses. Either way, you should get the same number, 8.5188. So mean and standard deviation can be used, which we'll use a little bit later, to make predictions if you have the mean and the standard deviation for a given sample size. Let's look at what a distribution histogram would look like given this same example. So using your calculator, binomial PDF, find the probability distribution, or fill in, the probability distribution for wireless only households in a random sample of 10. So we're going to assume that same proportion, 41%. We're going to do a binomial PDF. So back to PDF. We have 10 trials, 41% chance of success, and our first x value is going to be 0. So round to 3 decimal places. And then what you can do is hit second enter and change the 0 to a 1. And we're doing this to get a histogram. So just round off to 3 decimal places. I won't make you do this on the test. I just want to show you what it looks like. So we're getting each individual outcome and its probability. We're just going to change that last number, change the target value as you go along, rounding to 3 decimal places. So we're going to change that 3 to a 4, 0.250, change the 4 to a 5, 0.209, Change the 5 to a 6. And we're gonna put mean and standard deviation together with what we're doing right now. I know that kind of seemed like it jumped, but it'll all come back together here in just a second. Change the 6 to a 7. Change the 7 to an 8. Change the 8 to a 9. And finally change the 9 to a 10. This probably is going to be pretty small. So on that last one, you get the e to the -4, so just remember to move that decimal place over 3 times. So you essentially get 0.000. Alright, so I've scaled the histogram for you. I'd like you to make a discrete histogram for each outcome. So for 0, it's 0.005, which is pretty small. For 1, it's 0.036, 0.111. Just kind of have to eyeball how this goes. For 3, it jumps up to 0.206. For 4, it jumps up to 0.25. For 5, it goes back down to 0.209. For 6, it goes all the way down to 0.12. For 7, it's right around 0.05. For 8, 0.013, pretty tiny. For 9, really tiny. And for 10, basically 0. So we have a mostly bell-shaped curve. It trails off a little bit, little skewed right, but mostly bell-shaped. You'll notice that it hovers around 4, and that's because our probability of success is 0.41 out of 10 trials, which is right around 4 successes is what you would expect. So that's our mean. And if we were to calculate the standard deviation, which we won't, but if we were, it would spread with that standard deviation. So everything we learned back in chapter 3 is coming back for this. You're centered and you have your spread, just like using these two calculations from up here. So we're going to kind of bring all this together. We don't go too far into normal distributions and binomials, but a little bit, just touching on it. The main idea is that the center is at the mean and that the spread follows that bell curve. So let's look at various histograms with, let's see, the first set has the same sample size and different probabilities. So your first histogram here has a sample size of 10 and a probability of success of 0.2. So if you were to quickly multiply those together, that would give you a mean of 2, and you'll notice that's where your tallest bar is. So these histograms did the same thing we just did, but with different probabilities. So you'll notice it's a little skewed right, kind of trails off to the right, because you have a low chance of success. The middle histogram has a sample size of 10 and a probability of success of 0.5. So you'll notice it's very bell-shaped. Your expected value falls right in the middle, and it's pretty symmetrical on either side. The next one also has a sample size of 10, but the probability of success is 0.8. So with a higher chance of success, the majority of the data hovers around 8, and it becomes a little bit skewed left. So those are the same sample sizes, but different probabilities of success. Now we're going to look at various histograms with the same probabilities and different sample sizes. So different sample sizes and the same probabilities. So this first distribution has a sample size of only 10 and a 0.2 chance of success, and they've kind of zoomed it out a little bit. So it's the same picture here, but they made the X scale a little bit bigger. So the majority of your data is kind of squished all around 2. The next distribution has a sample size of 30 and a probability of success of 0.2. If I were to do 30 times 0.2, I get 6. So you'll notice the majority of the data is centered around 6, and it gets a little bit more bell-shaped, a little bit more even on both sides. The last distribution has a large sample size of 70 and a probability of 0.2. If I were to do 70 times 0.2, you'll notice the center should be around 14. So there's 14, it spikes, and it has a very bell-shaped distribution on either side. So it's very nicely bell-shaped. So I wanted to show you all of these to talk about, for a fixed probability, like these last three, where the probability is the same, as the number of trials in the binomial experiment increases, gets bigger and bigger and bigger, the probability distribution of the random variable x becomes bell-shaped. And we like bell-shaped data. That's what we like to focus on. So we said that in this class we focus on bell-shaped data. We don't worry about skewed data. So these skewed graphs aren't going to do us any good. We want these nice bell-shaped distributions. So as a rule of thumb, if n times p times 1 minus p is at least 10, 10's the magic number there, the probability distribution will be approximately bell-shaped. So we don't have to sit here and make those histograms. We can say that if we do this check, if we do n times p times 1 minus p, which is the part under the square root for the standard deviation to help you remember that, if that, before you square root it, is at least 10, the probability distribution will be approximately bell-shaped, which is what we want. So this helps us distinguish between usual and unusual events. Statistics is always focused on, did we expect that outcome or is something weird going on? And that's the focus for the second half of the course. Is this something that we expected to happen kind of in the middle of the curve, or is this something unusual, weird going on at the ends or tails of the curve? So if the distribution is approximately bell-shaped by testing n times p times 1 minus p being at least 10, then we can use the empirical rule to make a decision. So what we're going to do is we're going to calculate the mean and the standard deviation to get this started. So it says this result allows us to use the empirical rule to identify unusual observations in a binomial experiment. Recall the empirical rule states that in a bell-shaped distribution, about 95% of all observations lie within 2 standard deviations of the mean. So what we're going to be doing is looking at the mean minus 2 standard deviations and the mean plus 2 standard deviations. Those are kind of our cutoff points. Any observation that lies outside of this interval may be considered unusual because it occurs less than 5% of the time. So we said that also in Chapter 5. Anything that occurs less than 5% of the time is considered unusual. Alright, so let's do an example of this. Again, we're just touching on this idea. Your book goes into further detail, but we don't go there in this course. Alright, so looking at example 8. We'll worry about the extra example later. We're going to use that same example. 41% of households are wireless only. In a random sample of 300 households, 143 of them were wireless only. So they actually went out, took a sample, figured out that 143 were wireless only. The question is this an unusual result? So the first thing we need to do is compute the mean and the standard deviation. For this example, we've already done that, so we can use our previous results. Normally, you would have to calculate that again, but we've already done that. We figured out the mean for a sample of 300 is 123, and the standard deviation for that sample, I'm going to call that 8.52. So normally you crunch those numbers, but we've already done that. And then, can we assume that this distribution is bell-shaped? So we need to check n times p times 1 minus p to make sure it's at least 10. So n was 300. Probability of success was 0.41, and then 1 minus 0.41. we need to make sure that that's at least 10. So let's do that. Let's do 300 times 0.41 times 1 minus 0.41. We get 72.57. It's at least 10, so we can say yes, this data is going to be roughly bell-shaped. So I like to draw the picture of the bell. That just helps me visualize what I'm doing. You don't have to, but it helps. So our sample was 143, and we want to know if that's more than 2 standard deviations above the mean. We said the mean was 123, so 1, 2. Standard deviation was 8.52, so I'm going to do 123 plus 8.52, that's 1 standard deviation. 131, and I'm going to add it again, which is about 140. Just kind of rounding there. So I add the standard deviation once and then again to get to 140.04. So that is the mean plus 2 standard deviations. And you can do that with or without the picture. I just like the picture. I think it helps. So our x value, what we actually observed, was 143. And you'll notice that 143 is beyond that 2 standard deviations. So it's in the unusual zone because it's beyond 140. So we can say yes, 143 is unusual. And then we'll talk about this more in chapter 7. But this is what statisticians do. They find the center, they find the spread, and then they check if individual values are in the middle, nothing weird's going on, or are they in the tails, either lower or upper tail, and something weird is going on. So in this case, because 143 is beyond that 2 standard deviation mark, we can say yes, that's an unusual event. Alright, the last part of this guided notes is an extra example. I actually pulled this right out of the textbook, right out of your homework, so you have this as a homework question. It's good practice, but I'm not going to go through it. If you do want the exact answers for this problem, just email me. But you do have these questions in your homework, so you can know right away if you're doing them right or not. You can always email anytime. And that is it for chapter 6.